My name is Stephen Hawking. I am a theoretical physicist and cosmologist, and I have spent my entire career studying the deepest mysteries of our universe. But today, I need to tell you something that might fundamentally challenge everything you think you know about human space exploration. For decades, we've been told that returning to the moon is simply a matter of political will and funding. We've been led to believe that the technology that took us there 50 years ago can easily take us there again. But what I'm about to share with you reveals a far more complex and troubling reality. The truth is that returning to the moon with current technology isn't just difficult, it's practically impossible, and the reasons why will shock you. When I first began studying physics in the 1960s, the Apollo program was humanity's greatest technological achievement. We had just witnessed 12 men walk on the lunar surface between 1969 and 1972. The entire world watched in awe as Neil Armstrong took that first historic step. But here's what most people don't realize about those missions. They weren't just dangerous. They were absolutely, catastrophically risky in ways that would never be acceptable today. Every single Apollo mission was essentially a controlled explosion, hurtling 3 men through the vacuum of space in what was, by today's standards, a primitive tin can. Let me put this in perspective for you. The Apollo spacecraft had less computing power than the smartphone in your pocket right now. The guidance computer that navigated those astronauts to the moon had exactly 72 kilobytes of memory. Your digital watch probably has more processing power than the computer that controlled humanity's greatest achievement. The margins for error were so thin that a single miscalculation, a single component failure, could have meant certain death for the crew. And we accepted those risks because we were in the middle of the Cold War, racing against the Soviet Union to prove our technological superiority. But today, we live in a completely different world. The tolerance for human casualties in space exploration has dropped to virtually zero. When the Space Shuttle Challenger exploded in 1986, killing 7 astronauts, it grounded the entire shuttle program for nearly 3 years. When Columbia broke apart during re-entry in 2003, killing another 7 astronauts, it led to the retirement of the entire shuttle fleet. Can you imagine the public outcry if we lost a crew on their way to the moon today? The political fallout would be devastating. Any space agency that experienced such a tragedy would likely see their funding eliminated and their programs shut down permanently. This shift in risk tolerance has created what I call the modern space paradox. We have better technology than ever before, but we're actually less capable of achieving the bold missions of the past because we can no longer accept the extreme risks that made those missions possible. The Apollo astronauts were test pilots, men who were accustomed to flying experimental aircraft with failure rates that would terrify us today. They understood that their missions had maybe a 50-50 chance of success, and they accepted those odds because the stakes were so high. During my 30-year career studying the fundamental laws of physics, I've learned that every space mission must overcome the same basic challenge that has remained unchanged since the dawn of the space age. Earth's gravity well is extraordinarily deep. To escape our planet's gravitational pull and reach the moon, you need to accelerate a spacecraft to a velocity of approximately 25,000 miles per hour. This requires enormous amounts of energy, and energy means fuel, and fuel means weight, and weight means you need even more fuel to lift that fuel. It's a vicious cycle that rocket engineers call the tyranny of the rocket equation. Here's the sobering mathematics of lunar travel that most people never consider. For every pound of payload you want to send to the moon, you need approximately 60 pounds of rocket fuel. Want to send 3 astronauts plus their life support systems, plus their lunar lander, plus enough fuel to get them home? You're looking at a total spacecraft weight of approximately 6,400,000 pounds at launch. That's the equivalent of 32 fully loaded Boeing 747 aircraft stacked on top of each other. And all of that mass has to be accelerated to escape velocity using chemical rockets that are fundamentally no more advanced than the fireworks invented by the Chinese over 1,000 years ago. The physics of chemical propulsion creates an absolute ceiling on what we can achieve. Chemical rockets can only reach a maximum exhaust velocity of about 4,500 meters per second. This is determined by the basic chemistry of combustion and cannot be improved no matter how advanced our engineering becomes. We've essentially reached the theoretical limits of chemical rocket performance. The Saturn V rocket that carried the Apollo missions to the moon was about as efficient as chemical rockets can possibly get. In the 50 years since Apollo, we've made incremental improvements in reliability and cost, but we haven't fundamentally changed the physics. You might wonder why we don't simply build another Saturn V rocket. After all, we still have the blueprints, don't we? Well, this is where things get truly alarming. The institutional knowledge required to build and operate the Saturn V has been almost completely lost. The engineers who designed it have retired or passed away. The manufacturing facilities have been dismantled. The supply chains that produced its millions of specialized components no longer exist. The industrial base that supported Apollo employed over 400,000 people across thousands of companies. That entire ecosystem has vanished. But even if we could somehow recreate the Saturn V, it wouldn't meet modern safety standards. The escape systems were primitive by today's standards. The heat shields contained asbestos, which we now know is carcinogenic. The computer systems couldn't interface with modern mission control software. The communications equipment is so obsolete that it couldn't operate with current NASA tracking networks. Every single system would need to be completely redesigned and retested, which would essentially mean building an entirely new rocket from scratch. This brings us to one of the most disturbing aspects of our current predicament. NASA has been trying to return to the moon for over 2 decades through the Constellation program, then the Artemis program. They've spent well over $100 billion on these efforts, and yet, as of 2025, we still don't have an operational lunar transportation system. The Space Launch System, NASA's new moon rocket, has experienced countless delays and cost overruns. Its first unmanned test flight finally launched in 2022, but the program is already years behind schedule and billions of dollars over budget. Let me share with you something that keeps me awake at night as a physicist who has devoted his life to understanding the cosmos. We are facing what I call the great filter of spaceflight. Every technological civilization may eventually reach a point where the easy achievements have been accomplished, but the next level of advancement requires resources and coordination that are beyond their political and economic capabilities. The moon landings may have represented the absolute peak of what a single nation can achieve through a massive, focused effort during a time of existential competition. Consider this sobering comparison. The Apollo program consumed approximately 4% of the entire United States federal budget for nearly a decade. In today's dollars, that would be equivalent to spending over $160 billion per year on lunar exploration. Can you imagine any modern democracy sustaining that level of spending on space exploration when they're facing healthcare crises, educational challenges, infrastructure decay, and climate change? The political reality makes such an investment virtually impossible. But the challenges go far deeper than politics and funding. The human body itself presents obstacles that we didn't fully understand during the Apollo era. Those missions lasted only 8 to 12 days. The astronauts experienced some radiation exposure and bone loss, but the effects were manageable. However, modern lunar missions would likely require much longer stays on the surface to justify the enormous cost. Extended exposure to lunar conditions creates medical problems that we're still trying to solve. The moon has no magnetic field and virtually no atmosphere, which means that astronauts are exposed to deadly cosmic radiation and solar particle events. A major solar flare during a lunar mission could deliver a lethal dose of radiation to an unprotected crew. The lunar dust is incredibly fine and abrasive, created by billions of years of micrometeorite impacts. This dust gets into everything and poses serious health risks when inhaled. It damaged equipment during every Apollo mission, and longer stays would only exacerbate these problems. The psychological challenges of lunar missions are equally daunting. The astronauts would be hundreds of thousands of miles from Earth, with communication delays of several seconds each way. If an emergency occurs, there is no possibility of rescue. The crew would be completely on their own in one of the most hostile environments imaginable. The isolation and stress could lead to mission-critical mistakes or psychological breakdowns. We've seen these effects in Antarctic research stations and on the International Space Station, but a lunar mission would be far more extreme. During my years of studying black holes and the fundamental nature of space-time, I've learned that the universe doesn't make anything easy. Every step forward in our understanding requires enormous effort and often reveals new complexities we never anticipated. The same principle applies to space exploration. As our knowledge has advanced, we've discovered that lunar missions are far more complex and dangerous than we originally realized. The life support systems required for modern lunar missions are incredibly sophisticated. The Apollo spacecraft had enough oxygen, water, and food for the planned mission duration, plus a small emergency reserve. But there was virtually no redundancy. If any critical system failed, the crew would likely die. Modern safety standards require multiple backup systems for every critical function. This redundancy adds enormous weight and complexity to the spacecraft. Water is perhaps the most critical resource for any lunar mission. Each astronaut needs approximately 4 gallons of water per day for drinking, food preparation, and hygiene. For a crew of 4 spending 2 weeks on the moon, that's over 200 gallons of water. But water weighs 8 pounds per gallon, so you're looking at over 1,600 pounds just for water. Then you need backup water supplies in case of contamination or system failures. The logistics quickly become overwhelming. Food storage presents another challenge that the Apollo missions barely had to consider. Those short missions relied on freeze-dried foods and energy bars. But longer missions would require much more varied nutrition to maintain crew health and morale. Fresh foods are heavy and spoil quickly. Advanced food preservation systems add weight and complexity. The psychological benefits of good food during a long, stressful mission cannot be underestimated, but providing it creates significant logistical challenges. The thermal environment of the moon is absolutely brutal. Lunar daytime temperatures can reach over 250 degrees Fahrenheit, while nighttime temperatures drop to minus 250 degrees Fahrenheit. This 400-degree temperature swing occurs over the course of a lunar day, which lasts approximately 28 Earth days. Protecting astronauts and equipment from these extreme temperatures requires sophisticated thermal control systems that add weight and complexity to every component. Let me tell you about a conversation I had with a former Apollo engineer several years ago that really opened my eyes to how much we've lost. He told me about the culture of the 1960s space program, where engineers were willing to work 18-hour days, 7 days a week, for years on end. They were driven by a sense of national purpose and competition that simply doesn't exist today. They made decisions quickly, accepted risks that would be unthinkable now, and moved forward even when they weren't entirely certain of success. That engineer described how they would test new components by actually flying them on missions, accepting that some failures were inevitable but could be corrected on subsequent flights. The Apollo 1 fire that killed 3 astronauts during a ground test led to design improvements, but they didn't stop the program. They learned from the tragedy and moved forward. Today, a similar accident would likely end any lunar program permanently. The manufacturing capabilities that supported Apollo have also largely disappeared. The specialized facilities that produced the F-1 engines for the Saturn V were dismantled decades ago. The skilled technicians who knew how to handcraft critical components have retired. The institutional knowledge of how to manage a program of that complexity has been lost. Modern aerospace projects are managed by committees and subjected to layers of oversight that, while well-intentioned, make rapid progress nearly impossible. I want you to consider something that most people never think about. The Apollo missions were essentially experimental flights masquerading as operational missions. Every single flight was testing new systems and procedures. The astronauts were test pilots, willing to risk their lives to push the boundaries of human capability. But modern space agencies operate under completely different principles. Every system must be thoroughly tested and validated before human flight. This approach is much safer, but it also makes bold missions incredibly expensive and time-consuming. The economic model that supported Apollo no longer exists. The space program of the 1960s was essentially a massive government jobs program that employed hundreds of thousands of people across the American South and West. Politicians supported it because it brought federal dollars to their districts. The Cold War provided the political justification for enormous spending. But today's space program must compete with countless other priorities for limited government resources. Private companies like SpaceX have made impressive progress in reducing launch costs, but they're still operating within the fundamental constraints of chemical rocket propulsion. Elon Musk's goal of making humanity a multiplanetary species is admirable, but the physics remains unchanged. Even with significantly reduced costs, lunar missions would still require enormous investments for uncertain returns. Here's something that troubles me deeply, as someone who has spent his career pushing the boundaries of human knowledge. We may have passed the peak of human space exploration capability. The Apollo program represented a unique convergence of political will, economic resources, technological capability, and risk tolerance that may never be repeated. We achieved something extraordinary, and then we walked away from it because the costs and risks were simply too great to sustain. The space stations we operate today, like the International Space Station, represent a different approach to space exploration. They're focused on scientific research and international cooperation, rather than bold exploration. They operate in low Earth orbit, just a few hundred miles above our planet, protected by Earth's magnetic field, and close enough for rapid evacuation if necessary. This is a much more sustainable model for space operations, but it's not the inspiring vision of human expansion that captured the world's imagination during Apollo. I think often about what it means for our species to have briefly touched another world, and then retreated. We proved that it was possible to leave Earth and survive, but we also learned that it's extraordinarily difficult and dangerous. The romantic vision of space exploration, where humans spread across the solar system like explorers crossing the ocean, crashes against the hard reality of physics and human biology. The distances involved in space exploration are almost incomprehensible. The Moon is our closest celestial neighbor, and it's still 238,900 miles away. To put that in perspective, if you could drive a car to the Moon at highway speeds, it would take you over 4 months of continuous driving to get there. And that's just to reach our cosmic backyard. Mars, the next logical destination for human exploration, is millions of miles away depending on the orbital positions of the planets. The energy requirements for interplanetary travel scale exponentially with distance and mission duration. A Mars mission would require approximately 3 years round trip and would face all the challenges of lunar missions multiplied many times over. The radiation exposure alone would likely exceed safe limits for human beings. The psychological stress of being isolated for 3 years with no possibility of rescue would push human endurance to its absolute limits. But perhaps the most sobering aspect of our space exploration predicament is what it reveals about the nature of technological progress. We tend to assume that technology always advances, that each generation can achieve more than the previous one. But the history of human civilization is filled with examples of technologies that were achieved and then lost. The Romans built concrete that was stronger than what we can make today. Medieval cathedrals required construction techniques that we struggle to replicate. The Apollo program may be another example of a technological achievement that exceeded our sustainable capabilities. This doesn't mean that human space exploration is finished forever, but it does mean that returning to the Moon will likely require revolutionary advances in propulsion technology, life support systems, and radiation protection. We may need to develop nuclear rockets, fusion drives, or other exotic propulsion systems that are currently beyond our technological reach. We may need to learn how to manufacture everything we need from lunar resources rather than transporting it from Earth. We may need to accept much longer mission durations and much higher risks than current safety standards allow. The path back to the Moon, if it exists at all, will likely require a different approach than the one that got us there the first time. Instead of massive government programs with unlimited budgets and acceptable casualty rates, we may need to develop sustainable, economically viable reasons for lunar presence. Mining lunar resources, conducting scientific research that can only be done on the Moon, or using the Moon as a stepping stone to Mars might eventually justify the enormous costs and risks. I believe that the real lesson of Apollo is not that we can achieve anything we set our minds to, but that we can briefly exceed our sustainable capabilities under extraordinary circumstances. The Moon landings were a magnificent human achievement, but they were also an anomaly that may not be repeatable with current technology and social constraints. As I reflect on my career studying the deepest mysteries of the universe, I'm struck by how the cosmos seems designed to keep us humble. Every answer we discover reveals new questions. Every technological achievement shows us how much more difficult the next step will be. The universe is not hostile to life, but it's certainly not hospitable either. It presents challenges that test the very limits of what intelligent beings can accomplish. The question that haunts me is whether human beings will remain trapped in Earth orbit for the foreseeable future. or whether we'll eventually develop the technologies and social structures necessary to become a true spacefaring civilization. The Apollo missions proved that it's possible to leave Earth, but they also demonstrated just how difficult and expensive it is to do so sustainably. Perhaps the most important thing we can learn from our current inability to return to the Moon is that we need to approach space exploration with much more realistic expectations about costs, risks, and timescales. The grand visions of space colonization that populate science fiction may be possible someday, but they will require technological revolutions that we can barely imagine today. The Moon remains tantalizingly close, a reminder of what we briefly achieved and what we've temporarily lost. Whether we'll ever return as anything more than occasional visitors remains one of the great unanswered questions of our time. The physics hasn't changed, but our capabilities and constraints certainly have. The next chapter in human space exploration will require wisdom, patience, and perhaps a tolerance for risk that our current civilization may not possess. What we've learned is that touching the stars, even our closest celestial neighbors, demands everything we have to give and more than we can sustain. The universe, in its infinite complexity and beauty, continues to challenge us to become better than we are. Whether we'll meet that challenge remains to be seen. The paradox of our technological advancement becomes even more apparent when you examine the specific engineering challenges that modern lunar missions must overcome. During my decades of research into the fundamental forces of nature, I've come to understand that complexity often grows exponentially rather than linearly. The Apollo spacecraft were essentially mechanical systems with minimal electronics. Today's spacecraft are flying computer networks with thousands of interconnected systems, each capable of catastrophic failure. Consider the software requirements alone. The Apollo guidance computer ran on approximately 8,000 lines of code. A modern spacecraft requires millions of lines of code to operate safely. Every line of that code represents a potential failure point that must be tested exhaustively. The verification and validation process for mission-critical software can take years and cost hundreds of millions of dollars. We've traded the simplicity that enabled rapid development for the complexity that ensures reliability, but that complexity has made bold missions almost impossibly expensive. I remember attending a lecture in the 1970s where a NASA engineer described how they solved problems during Apollo. When something didn't work, they would gather the brightest minds in a room, brainstorm solutions for a few hours, build a prototype overnight, and test it the next day. If it worked, they would implement it. If it didn't, they would try something else. The entire development cycle from problem identification to solution implementation could happen in days or weeks. Today, that same problem would trigger a formal review process involving multiple committees, extensive documentation, risk assessments, environmental impact studies, and months or years of deliberation. The solution would need to be designed, modeled, simulated, tested, retested, reviewed, approved, manufactured, quality controlled, and validated before implementation. This process produces much more reliable results, but it also makes rapid innovation nearly impossible. The materials science challenges alone illustrate how much more we now know about the dangers of space exploration. The Apollo lunar modules were built primarily from aluminum alloy, which we now know becomes brittle when exposed to cosmic radiation. The thermal protection systems used asbestos insulation, which poses serious health risks. The electrical systems had minimal protection against electromagnetic interference from solar flares. By today's standards, those spacecraft were death traps that somehow managed to work long enough to complete their missions. Modern spacecraft must use advanced composite materials that can withstand decades of radiation exposure without degrading. They need sophisticated shielding to protect electronics from electromagnetic interference. They require redundant life support systems that can operate reliably for months or years without resupply from Earth. Every component must be designed to last far longer and operate much more reliably than anything the Apollo program required. The human factors engineering requirements have also expanded dramatically. We now understand that prolonged exposure to microgravity causes significant bone loss, muscle atrophy, cardiovascular deconditioning, and vision problems. Astronauts on the International Space Station exercise for 2.5 hours every day just to maintain basic physical health. A lunar mission would require sophisticated exercise equipment, medical monitoring systems, and possibly artificial gravity generation through rotation. The psychological support requirements are equally demanding. Apollo astronauts were selected specifically for their ability to remain calm under extreme stress and work effectively in isolated, dangerous environments. But even they experienced significant psychological stress during their brief missions. Modern understanding of human psychology suggests that longer missions would require much more sophisticated crew selection, training, and support systems. Let me tell you about a conversation I had with a psychologist who studies extreme environment behavior. She explained that humans can tolerate almost any hardship if they believe it's temporary and meaningful. The Apollo astronauts knew they would be home in a week or two, and they were participating in one of the most significant events in human history. But modern lunar missions might require stays of 6 months or more, and the novelty has worn off. The psychological challenges of long-duration lunar missions may be even more difficult to overcome than the technical challenges. The regulatory environment for space exploration has also changed dramatically since Apollo. In the 1960s, NASA operated with minimal oversight and could make decisions quickly. Environmental protection laws didn't exist. Safety regulations were minimal. International space law was virtually non-existent. Today, any major space mission must navigate a maze of federal regulations, international treaties, environmental impact assessments, and safety requirements that can add years to development timelines. The manufacturing base that supported Apollo was fundamentally different from today's aerospace industry. The 1960s space program operated like a wartime production effort, with cost being a secondary consideration to speed and performance. Companies would bid on contracts knowing they would lose money because the prestige and technical knowledge gained were considered sufficient compensation. Today's aerospace industry operates on much thinner profit margins and cannot afford to take on unprofitable contracts for patriotic reasons. The supply chain complexities are staggering. A modern spacecraft contains components from hundreds of suppliers across dozens of countries. Each component must meet strict quality standards and undergo extensive testing. The lead times for specialized components can be years. Managing this global supply chain while maintaining the security and reliability requirements for human spaceflight creates logistical challenges that didn't exist during Apollo. I've spent considerable time thinking about what this means for humanity's future in space. We may be entering what I call the sustainable space age, where we focus on missions that provide clear economic or scientific returns rather than symbolic achievements. The International Space Station, for all its limitations, represents a more realistic model for human space presence. It operates continuously, provides valuable scientific research, and has been incrementally improved over decades. Commercial space companies are beginning to develop lunar capabilities, but their approaches are fundamentally different from Apollo. They're focused on robotic missions initially, with human missions only when they can be justified economically. SpaceX's Starship, if it works as designed, could potentially reduce the cost of lunar missions by an order of magnitude. But even with dramatically reduced costs, human lunar missions would still be enormously expensive and risky undertakings. The international cooperation model may be more sustainable than the national competition model that drove Apollo. The International Space Station has demonstrated that countries can work together on complex space projects despite political tensions on Earth. A multinational lunar base might be politically and economically feasible in ways that a purely American or Chinese lunar program would not be. But we must also confront the possibility that human space exploration may remain limited to Earth orbit for decades or even centuries. The physics of space travel, the biology of human survival, and the economics of complex missions all argue against rapid expansion into the solar system. We may need to accept that Star Trek-style space exploration belongs to science fiction rather than near-term reality. This doesn't diminish the importance of space exploration, but it suggests we need more realistic expectations about what's possible with current technology. Robotic missions can accomplish most scientific objectives at a fraction of the cost and risk of human missions. The James Webb Space Telescope has revolutionized our understanding of the universe without requiring a single human to leave Earth's surface. The question that keeps me awake at night is whether our brief visit to the Moon represents the high watermark of human space exploration, or whether it was simply the first tentative step toward becoming a spacefaring civilization. The answer may depend on whether we can develop revolutionary new technologies that make space travel fundamentally easier and safer than it is today. Fusion rockets could potentially provide the enormous energy density needed for efficient space travel. Advanced life support systems might allow humans to survive in space for years without resupply. Artificial intelligence could manage the complexity of modern spacecraft systems. Space-based manufacturing could eliminate the need to transport heavy equipment from Earth's surface. But all of these technologies remain decades away from practical implementation, if they're possible at all. We may be at a technological plateau where the next major advances require scientific breakthroughs that we cannot predict or schedule. The history of technology is filled with long periods of incremental improvement, punctuated by sudden revolutionary changes that nobody saw coming. What I can say with confidence is that returning to the moon with current technology would be an extraordinary achievement that would push human civilization to its limits. It would require international cooperation, sustained political commitment, massive financial investment, and acceptance of risks that our current society finds difficult to tolerate. Whether we have the collective will to undertake such an effort remains an open question. The moon continues to orbit overhead, a constant reminder of what we briefly achieved and what remains tantalizingly out of reach. It represents both our greatest triumph and our most sobering limitation. Whether future generations will walk on its surface again depends on choices we make today about how much we're willing to sacrifice for the dream of becoming a spacefaring species. The universe, in all its vastness and complexity, does not make anything easy for us. Every step forward requires enormous effort and often reveals new obstacles we never anticipated. But that has never stopped humans from pushing forward, from attempting the impossible, from reaching toward the stars even when the stars seem impossibly far away. Perhaps that stubborn refusal to accept limitations is the most human trait of all, and perhaps it will eventually carry us back to the moon and beyond, no matter how difficult the journey may be.